In 1941, Chrysler bolted 5 car engines together and called it a tank motor. 30 cylinders, 21 liters, 5 carburetors, 5 distributors, 5 sets of spark plugs, and one enormous headache for every mechanic who ever had to touch it. It weighed more than 2.5 tons, and somehow, against every reasonable expectation, it worked. The story of how that happened starts with a phone call. In the summer of 1940, William Knudsen, who was running the Office of Production Management for the federal government, picked up the phone and called his old friend K.T. Keller, president of Chrysler Corporation. Knudsen had one question: can you build tanks? Keller's answer was honest. He said he didn't know. He'd never seen one, not a model, not a photograph he'd studied closely. Nothing. So they flew him out to Rock Island Arsenal in Illinois, put him inside an M3 Lee, and drove him around the proving grounds. Keller climbed out, looked at his chief engineer Eddie Hunt, and said, "Yeah, we can make these. How many do you need?" That's how the largest tank manufacturer in America got its start. A car company president who had never laid eyes on a tank agreeing to build 1,000 of them. The next day, Keller assembled a team. By the end of that week, they'd been to Washington, seen prototypes in Illinois, and started studying 186 pounds of blueprints. Within weeks, Chrysler had signed a government contract. They set a price of $33,500 per tank, in 1940 dollars. The government bought farmland in Warren, Michigan, just north of Detroit. 113 acres. The factory was designed by Albert Kahn, the architect who had basically built industrial Detroit. Ford's River Rouge, General Motors headquarters, dozens of others. The plan was to apply automobile mass production principles to tank building, something nobody in the world had ever done before. The factory was called the Detroit Tank Arsenal. Construction started in the winter of 1940, and the first M3 tank rolled off the assembly line before the walls of the building were even finished. Workers wore coats and gloves on the factory floor because the heating plant wasn't done yet. They brought in a rented steam locomotive just to blow warm air through the unfinished building during the brutal Michigan winter. By April 1941, the governor of Michigan was watching the first tank fire its guns and smash through telephone poles at the dedication ceremony. 2,000 people attended. The building wasn't fully constructed. That was the kind of urgency driving everything. We cover this kind of engineering history every single week. Engines, tanks, aircraft, weapon systems, the disasters, and the breakthroughs. If that sounds like your thing and you're not subscribed yet, go ahead and do that. Now, back to the problem. Now, to understand what comes next, you need to understand 1941 America. The country was not officially at war yet, but everyone paying attention knew it was coming. Roosevelt had declared America the arsenal of democracy. Factories that had been making sedans and pickup trucks were being asked to think about building weapons. Chrysler alone was already running over 30 different military projects out of its 6-story engineering complex. K.T. Keller never turned down a single government request, not one. That was just who he was. A man who'd started as an apprentice with no formal engineering education and worked his way to the presidency of one of America's biggest corporations through pure mechanical intuition and relentless drive. When the government asked, Keller said yes first and figured out how later. He would go on to oversee not just tank production, but also Chrysler's top-secret work on uranium diffusers for the Manhattan Project. The same company, building tanks and helping build the atomic bomb at the same time. So the tanks were rolling off the line. Hulls, turrets, armor plate, all flowing through the factory at rates that would have been unimaginable 2 years earlier. But there was a crisis building behind the scenes: engines. You can build tank hulls and turrets all day long, but without engines, all you've got is very expensive steel boxes sitting on a factory floor. The standard power plant for American medium tanks was the Continental 975, a 9-cylinder air-cooled radial originally designed for aircraft. It made around 350 to 400 horsepower, decent motor, reliable enough once you understood its quirks. But the aviation industry also needed radial engines, desperately. The Army Air Corps was expanding at a ferocious pace, and every radial engine that went into a tank was one that didn't go into a trainer aircraft or a bomber. The numbers were staggering. In April 1941, the production plan called for 1,000 tanks per month. By July, that number had doubled. 2,000 medium tanks per month, each one needing a suitable engine. The Continental Radial simply could not be produced in those quantities while simultaneously feeding the insatiable demand from aviation. And the Navy's demand for diesel engines was eating into the supply of GM 671 truck engines that could have been paired for tank use. The Canadians were using them in their Valentine tanks. The Navy had placed enormous orders for the Marine version. There just weren't enough engines to go around. So the Army asked several manufacturers to come up with alternative power plants, fast. Ford developed the GAA, a massive 1,100 cubic inch V8 that would become the preferred American tank engine. General Motors offered their twin diesel setup. Both were conventional solutions. Chrysler's solution was not conventional. It was not reasonable. It was, by any traditional engineering standard, borderline insane. The idea came from Chrysler's executive engineer, Harry Wilson, and the engine design department headed by Mel Carpentier. They looked at what Chrysler had available in quantity, what they could build right now with existing tools, existing production lines, and existing workforce knowledge. The answer was the 251 cubic inch flathead inline six, a passenger car engine, the kind of motor that powered Chrysler Royals and Windsors on American highways. Reliable, simple, well understood. It made about 115 horsepower in civilian trim. One of those was obviously not going to move a 30-ton tank anywhere. Two of them wouldn't either. So they decided to use five passenger car engines, arranged in a star pattern around a common cast-iron crankcase, 30 cylinders total, 1,253 cubic inches, 21 liters of displacement. The thing looked like someone had grabbed a handful of engines and squeezed them into a ball. It wasn't a radial. It wasn't a V configuration. It wasn't a W. It wasn't anything that had existed before or has existed since. The bottom two engine banks sat angled 7.5 degrees above horizontal. The next two banks sat at 27 degrees above horizontal. The fifth bank sat straight up on top, pointing at the sky. 5 separate crankshafts, each driving a herringbone gear that meshed with a central sun gear on a common output shaft running through the central crankcase. 5 individual Carter TD, 1 single barrel carburetors, 5 distributors, 5 complete ignition systems, 1 shared oil pan, 1 massive radiator, 2 oil pumps, 1 for scavenging and 1 for pressure, both driven off the central gear train, and 30 cylinders worth of problems to sort out before any of it could go into a tank. The whole assembly weighed 5,244 pounds with the radiator, cooling fan, and clutch. That is 2.5 tons. Just the engine package. The logic was brutally practical. Chrysler already had the tooling for the 251-6. The production lines were running. The machine tools were set up and calibrated. The workforce knew how to build these engines in their sleep. Designing a completely new high-horsepower tank engine from scratch would take 2 to 3 years minimum, years they didn't have. Pearl Harbor was weeks away, so instead of reinventing the wheel, they took 5 existing wheels and bolted them together with a gear train. Development to first running prototype took roughly 4 months. 4 months from concept sketch to a functioning 30-cylinder engine. The test motors were ready for tank installation by mid-November 1941. The first M3A4 Lee tank with an experimental A57 went to Aberdeen Proving Ground for tests in February 1942. A pilot M4A4 Sherman followed in May. by June, the first production M3A4s were rolling out, 109 of them in total, and then the line switched to M4A4 Shermans, from initial concept to production tanks in under a year. That's not normal, that's wartime. That's what happens when bureaucracy gets out of the way and engineers get told to just make it work. But making it run was one problem. Making it run reliably was a completely different beast. The early A57 engines had serious issues. The biggest nightmare was overheating. The original design used 5 separate belt-driven water pumps, 1 per engine bank. They failed constantly. The radiator area was poorly sealed, allowing grease, dirt, and sand to foul the cooling fins and choke airflow. And here was a problem nobody had fully anticipated. The engine blocks had been designed to sit level in a passenger car. Now, 2 of them were tilted 7.5 degrees. 2 more were tilted 27 degrees. The water jackets inside the blocks weren't drilled for these new angles. Coolant pooled in some areas and starved others. Hot spots developed. Generators failed. Auxiliary components gave out at alarming rates. And the engine compartment was so tightly packed that working on anything significant required removing the entire 5,000-pound engine assembly from the tank. Chrysler had at least thought of that part. They built massive lifting eyes into the common crankcase specifically to help with engine extraction. But even with lifting eyes, pulling and reinstalling a 2.5-ton engine in a field depot under time pressure was not anyone's idea of a quick repair. In October 1942, 5 M3A4s and 5 M4A4s were sent to the California desert for testing. This was a monstrous test for vehicles with a cooling system that was already struggling in temperate conditions. The results were brutal. Constant breakdowns. Overheating in the harsh desert heat exposed every single weakness in the design. The Army's verdict was straightforward. Unsatisfactory for use in combat. Done. They wanted nothing to do with the A57. The U.S. Army made up its mind, and they made it up fast. The Multibank was a dead end. They tried offering the M4A4s to the Marines. The Marine Tank School kept them for about 2 months before sending them back. No thanks. The Army relegated the entire fleet to training duty inside the continental United States. No combat deployment, no overseas shipment, just practice vehicles for crews who would eventually fight in tanks with different engines. The plan was to phase the A57 out entirely as soon as enough Ford GAA V8s and Continental radials became available. But there was a catch, a big one. Tank production goals for 1942 were enormous, and the Detroit tank arsenal was already tooled up and running M4A4s on the line at full speed. In December 1942 alone, 5,000 workers at the arsenal set an all-time monthly record by producing 907 Sherman tanks. Shutting down that production line to wait for different engines would mean falling catastrophically behind on numbers. Numbers the Allies needed to survive. So the A57 stayed in production, an engine nobody in the American military wanted, being built by the thousands, powering tanks that the Army refused to send into combat. This is wartime manufacturing. You don't get to wait for perfect. You ship what you've got and fix it later. And Chrysler did fix it. They attacked every failure systematically. The 5 individual water pumps were scrapped and replaced with a single gear-driven unit that fed all 5 engine banks from one reliable source. The radiator sealing was completely redesigned. The water jackets on the angled engine blocks were re-drilled to improve coolant flow at their actual operating angles. Distributor and ignition systems were refined and simplified. But the most critical breakthrough came from studying exactly what broke during those endurance tests. The Army's engineers discovered that the vast majority of mechanical failures in the A57 came down to 2 specific components: piston rings and exhaust valves. The original piston rings wore out too fast under sustained high-load operation. The exhaust valves couldn't handle the continuous high temperatures of a tank engine, running at near full power for hours on end, day after day. Chrysler's solution was borrowed directly from aircraft engine technology. They installed chrome-plated top piston rings and stellite-faced sodium-cooled exhaust valves. Sodium-cooled valves use a cavity filled with metallic sodium that melts during operation and sloshes back and forth, transferring heat from the valve face up through the stem and into the cylinder head. It's a proven technique for high-temperature durability, standard in aviation, but unusual in ground vehicle engines at the time. The transformation was dramatic. After these improvements, 4 A57-equipped tanks were run through the Army's grueling 400-hour, 4,000-mile endurance test. One engine had a single failure. The other 3 completed the entire test without incident and with less than 10% power loss. Later testing showed even better results. One engine ran 339 hours before any breakdown. 3 others went the full 400 hours clean. Comparative reliability data from 1944 put the A57's average service life at 240 hours, second only to the Ford GIA at 255 hours, and ahead of both the GM Diesel at 225 hours and the Continental Radial at 218. The engine that had been declared the worst Sherman power plant was now near the top of the class. Now let's dig into the technical specifics. The compression ratio was set at 6.2 to 1, down from 7 to 1 in civilian form. Deliberate. Battlefield gasoline was 80 octane at best, sometimes considerably worse. High compression on low octane fuel produces detonation, and detonation destroys pistons. So Chrysler sacrificed some thermal efficiency for the ability to run on whatever fuel was available in a combat zone. Total output was 425 gross horsepower and 1,060 pound-feet of torque at 2,400 revolutions per minute. Net horsepower, accounting for accessories, was 370. For comparison, the Ford GAA made 450. The Continental Radial made 350 to 400. The A57 sat in the middle on horsepower, but delivered the most torque of any Sherman engine. Over 1,000 pound-feet at moderate RPM. For a tank weighing close to 35 tons fully loaded, that low-end grunt genuinely mattered for climbing hills and pushing through soft ground. The fuel metering problem deserves mention. Getting 5 separate carburetors to deliver precisely equal fuel-air mixtures through a common throttle linkage was a genuine engineering challenge. If one bank ran lean while another ran rich, you got uneven power delivery across the 5 crankshafts. Uneven power meant uneven loading on the herringbone gears. Uneven gear loading meant accelerated wear on the most critical and least replaceable component in the whole assembly. A Chrysler fuel systems engineer named Bert Dickinson was brought in after other engineers had spent weeks stuck on this problem. It took him about a week to solve it. The specific details of his solution have been lost to history. But the engine ran smoothly afterward. The physical dimensions tell you everything about the packaging challenge. 54.5 inches long, 56.5 inches tall, 58 3/4 inches wide, nearly 5 feet in every direction. A dense cube of cast iron that weighed 5,400 pounds, dry. Add 32 quarts of engine oil and a full cooling system, and you're well past 2.5 tons. This assembly was so large it required a custom-lengthened Sherman hull, 11 extra inches in the engine compartment, a blister in the floor for the cooling fan, a rectangular bulge across the top rear deck near the turret. The suspension bogies had to be moved farther apart to balance the longer hull. That wider bogie spacing is the easiest way to identify an M4A4 from across a field. On standard Shermans, the gap between bogies is about 1/3 of a road wheel diameter. On the A4, it's double that. And then there's the famous claim. Chrysler ran an advertisement in the February 1944 issue of Popular Science magazine, stating that the A57 could still move the tank even if 12 of its 30 cylinders were knocked out, 40% of the engine disabled. And the tank still drives. Some sources say it operated with 2 engine banks completely dead. Others claim 3 banks could fail, and the remaining 2 would still produce enough power to move. The truth sits somewhere in that range. But the principle is real, and it comes directly from the architecture. Each engine bank was essentially independent, its own fuel system, ignition, crankshaft, and gear feeding into the central sun gear. Lose a bank, and the remaining banks kept pushing power through the gear train. Less power, yes, possibly much less, but the tank moved. In combat, that difference is everything. The U.S. Army rejected it. The Soviets received 2 M4A4s for evaluation and turned them down flat. In September 1942, a Soviet delegation had visited the Detroit tank arsenal. They were shown 2 A57 engines running on endurance tests, one at 300 hours continuous, the other at 400. An American colonel tried to convince them to accept M4A4s instead of the M4A2s they preferred. He even pointed out that the M4A2 was at risk of cancellation due to engine supply problems. The Soviets weren't interested. They wanted diesel. Their entire supply chain ran on diesel. Their gasoline was low octane, and when the 2 test M4A4s finally arrived in the Soviet Union in late 1943, the Soviets drove them around, looked at the engine, and said no. Too complicated, too thirsty, not compatible with their logistics. The Marines sent theirs back after 2 months. The A57 was an orphan, but the British took them. Nearly 8,000 M4A4 Shermans went to Britain under Lend-Lease. The British called them the Sherman 5. And here is where the story turns completely. The engine America rejected became one of the most reliable power plants in British armored service. British data showed the M4A4 had a mean distance between major refurbishments of 4,000 kilometers. The M4A2 averaged 3,200. The tank the Americans didn't want was more reliable than the one they preferred. Chrysler sent technical representatives to England to train British crews. The crews learned the engine's quirks and adapted. The British approach was pragmatic. They understood that the A57 was complicated, but they also understood that complicated didn't mean unreliable if you knew what you were doing. They set up dedicated depot facilities where engines could be pulled, rebuilt, and returned to service efficiently. They developed procedures and trained specialists. And they found something the Americans had missed in their rush to judge the engine. The maintenance time on the Multibank was actually lower than on competing engines for routine work. A later comparative test of 20 Shermans found that M4A4 crews spent an average of just 45 hours on engine maintenance, compared to 110 hours for the Ford GAA in the M4A3, 132 hours for the Continental Radial in the M4A1, and 143 hours for the GM diesels in the M4A2. The A57 was the easiest engine to maintain. Its problem had never been routine servicing. Its problem was that when something major broke, you had to pull the whole thing. The British accepted that trade-off, and the motor that couldn't survive the California desert ran reliably across Normandy, through France, and into Germany. The M4A4 became the primary platform for the Sherman Firefly, the British variant mounting the 17-pounder anti-tank gun. In 1944, the Firefly was the only Allied tank that could reliably penetrate a German Panther or Tiger from combat range. Think about that for a second. The most lethal anti-tank version of the most important Allied tank of the war was powered by an engine that the country that built it refused to use. German crews were ordered to target Fireflies first. They knew what that longer barrel meant. British tankers camouflaged the barrel tip, painted fake muzzle brakes on the shorter mantlet, did anything they could to avoid being singled out. A 1944 British armored squadron had 1 Firefly per troop of 4 Shermans. That one Firefly was the only tank in the troop that could kill a tiger frontally. It was the most valuable vehicle on the field, and its engine had 5 carburetors. Roughly 2,000 Fireflies were built. The Sherman VC, based on the M4A4 hull, was the most common type, powered by 30 cylinders of Chrysler engineering and held together by herringbone gears and the sheer stubbornness of British mechanics who refused to let a complicated engine beat them. Between April 1942 and September 1943, Chrysler produced 9,965 of 57 engines. 7,500 went into production tanks. The rest were spares. The M4A4 served with more nations than any other Sherman variant: Britain, Canada, South Africa, New Zealand, Free France, Free Poland, Czechoslovakia, India, China. After the war, about 200 Fireflies ended up in Argentina, serving until the mid-1970s, before the A57 engines were finally swapped out for Ford V8s. Today, a handful of A57 engines survive, scattered across museums and private collections on 2 continents. The Imperial War Museum at Duxford has one. The Tank Museum in Dorset has 2, both in storage in the Conservation Centre, one acquired in 2019 from the UK Defence Academy at Shrivenham. A few restored tanks still run on their original A57 engines, including an operational M4A4 at the Wheels of Liberation collection in Gettysburg, Pennsylvania. Anyone who has ever kept one of these running deserves a certain kind of respect. You're maintaining a 30-cylinder engine built from 1940s car parts with tooling that was scrapped decades ago, using specifications from a motor that was only in production for 18 months. The people who do it are a particular breed. They're keeping alive something that was never supposed to last this long. An engine designed as a desperate stopgap, built from whatever was on the shelf, meant to fight a war and then be forgotten. The fact that any of them still turn over is a testament to either the original engineering or the stubbornness of the people maintaining them. Probably both. The A57 Multibank sits in a strange place in engineering history. It wasn't elegant. It wasn't efficient. It was heavy, complicated, and brutal to service. Born from desperation, designed in weeks, improved under pressure, rejected by its own military, shipped to an ally, and proved itself on the battlefields where the war was decided. 5 car engines bolted to a common crankcase, driving a Sun gear through herringbone gears, pushing a 35-ton tank across France. Not pretty, not ideal. But when a Sherman Firefly knocked out a tiger in the hedgerows of Normandy, there's a fair chance an A57 was keeping the lights on behind that turret. 30 cylinders, 5 carburetors, and somewhere in England, a maintenance crew that had learned to love it anyway. That's the story of the 30-cylinder Frankenstein engine, the motor America built, rejected, and handed to the British, who rode it to Berlin. If you've seen one in person, or you think I got something wrong, tell me about it in the comments. And if you made it this far, go ahead and subscribe. We do this every week,